In this video, we're going to discuss a phenomena with waves called the Doppler effect. This is not an interference phenomena like beats or standing waves was. Instead, this is just the impact of having a wave source, whether or not it's a light wave or a sound wave, that is either moving itself or that the observer is moving towards. In either of those cases, we will get the Doppler effect. So let's just see why that is. And looking first at a stationary source. So let me just label this as a stationary source. And we'll focus on sound because we are in mechanics. And so that is the type of Doppler effect that we're going to see the most examples of. And so what we have here is just a sound wave, and let's just say it's emitting a wave, kind of symmetrically around it. So that last one was a little wobbly. So these are going to be the sound waves that are emitted. There would be some, constant wavelength here that is related to the speed of the wave, right? So the wave speed is just what we're going to call v in our equations for the Doppler effect. And that would correspond to some spacing of these waves. And so if we imagine then that we can have then a moving source, and let's say that the source is moving with some speed vs. So let's make the source move in that direction, v sub s. So then what's going to happen is all of the waves are going to kind of build up on each other in the direction of motion and then spread out behind it. So I'll try to draw this here. So those circles will then no longer be concentric, right? Because the source has been moving as it's been emitting them. And so what happens then is we get these sort of non-concentric circles where in front of the source, we have a much smaller spacing. So we would actually observe, in this case, the higher frequency. So you would observe a higher frequency in front of the moving source if it's approaching. And then over here, and again, those are meant to be equally spaced. Here, the observer would have a lower frequency behind the source, meaning that it's moving away from you. So depending on whether it's coming towards you or coming away from you, you perceive a different sound. And that is fundamentally what the Doppler effect is. With light waves, that's be the red shift or the blue shift, which way, instead of the higher or lower pitch, like for sound waves, it would be whether it gets shift towards the blue side, the red side of the spectrum. But it is this fundamental shift in the observed frequency of the wave based on whether the source is moving towards you or away from you. So we can also say that basically the same thing will happen if the source is stationary, but you're moving towards it. So let's just, for good measure, let's look at that example. Let's just say that we have a moving observer, which has some speed v sub o for observer. And so in this case, I would have the stationary source with my concentric sound waves that are being emitted. And then I would have my observer here that then would stay running really fast towards the sound source, or in a car moving towards the sound source, or if it's a siren being emitted at a train station and the train approaches and versus leaves, then you have these sort of examples where you would actually hear this as an observer. So we'll give the observer some speed. The observer runs towards it. And again, what you can imagine is that as they run towards the source, then all of those waves, squish upon themselves. And again, you perceive in that case, the shorter wavelength would be the higher frequency. So you would perceive a higher frequency. And if you run away from it, then you would perceive a lower frequency. But so these phenomena can be observed with sound in our everyday lives. So let's take some examples of that. So these are audio examples. So you will want to have your volume up. And what you're going to notice is that as a sound source approaches, then you are going to hear a higher frequency. And then as it leaves, you're going to hear a lower frequency, just like we saw should happen when we looked at the shape of the waves as it approaches versus leaves. So here's a simple example with the car horn. Again, we can hear that just as it passes you, you hear that shift in the frequency from a high frequency, the observed high frequency as it approaches you, to the low frequency as it's going away. If you were in the car, you would hear something in between where the real frequency that it's being emitted is actually something different. So to calculate the Doppler shift, as we can see, it matters whether or not the source is moving towards us or away from us. That would change the shift, change the frequency that we hear. And it matters whether or not us, the observer, are moving towards or away from the source. And potentially you could have these two things happening at once. Maybe the source and the observer are moving towards each other, or maybe the source is approaching the observer, but the observer is trying to run away from it, right? So you have all of these different combinations. So the equation for the Doppler shift is best summarized by this table from that OpenStax textbook. And this is the general equation for the Doppler shift, where you do have those plus minus and the minus plus signs to indicate all of these different possibilities. And so let me just make sure that we know what these values are. FO is the observed frequency. That's what we hear, right? That's what we're perceiving. That is our observer frequency. That's what we hear. Fs is the frequency of the source. So that's the actual frequency emitted by the car horn, for example. And then we've already also defined V. So we have those two things. We have V, which is the speed of the wave speed. And so that's just the basic wave speed, the speed of sound, for example, 344 meters per second if it's a sound wave in air on a regular day. VO is the observer speed. Not velocity, because it's just going to be how fast they're going, and the plus or minus sign takes care of which way. And same thing for VS, that's going to be the source speed. So this equation here is used, the plus or minus signs as shown in the table here, where you can decide, for example, let's say that you have a stationary observer with a source moving towards the observer, then there is actually no VO, there's no observer speed, so it's 0. And then on the bottom, you would use a negative sign because you need to have a higher frequency, right? So you can reason your way through the plus and minus signs, or you can revert to using this table in order to figure them out. So this table is also included as an image in the module itself, or you can copy it down into your notes. Okay, so that concludes our video on Doppler effect.